In this video, I'm going to review some of the ways in which data variability is quantified. And we begin here with something called the range. And the range refers to the numerical distance between the two most extreme scores in a distribution. And what the range allows, it measures the total amount of spread that exists in the data. And mathematically, it's just simply calculated as the highest score, the greatest score among a group of numbers, subtract the lowest score in that group of numbers. And that provides us with the range of the data. Now, the range is considered a crude measure of variability and the simplest one to calculate. If our data is in the form of nominal or ordinal data, then the range is the only measure of variability that can be used. The range for interval or ratio data is actually helpful as the first type of variability to calculate because it will identify any possible mistakes that have been made in data entry if there is a very large deviating score that's not expected to be among that data set. So the range does have utility for interval and ratio data as well. But when we have ratio and interval data, the variance and the standard deviation are the two accepted means to quantify variability for, once again, interval or ratio data. And the variance and the standard deviation is a way to describe differences between scores. And what it does is it calculates one number that characterizes for all of the data how much spread exists among all those numbers. And the variance and standard deviation is typically based upon the normal distribution. In other words, when we talk about the variance and the standard deviation, we do so with respect to the average value of those numbers or the mean. And to begin this study of the variance and standard deviation, we begin with a basic concept called a deviation. And a deviation just refers to numerically how far or the distance between a single number of a group of scores resides from the average value of those numbers or the sample mean. The magnitude of a score's deviation is typically referred to as an error. Now, the error here does not necessarily imply a mistake. The term error here is used to indicate a value that deviates from the average, and we put a numerical value to it. So the way in which the deviation is calculated is that we take a single score. So if we have a collection of 30 numbers, X just represents one of those numbers, while X bar represents the average of those 30 numbers. And we just simply take the first score of those 30 numbers, we subtract the average score, and that gives us a deviation, how far away that number is from the average. Now, we don't change the order in which we carry out this subtraction. So of those 30 numbers, we will have 30 deviation scores. Approximately half of those deviation scores will be positive, and the other half will be negative. So the 2 points about the deviation, it's important to maintain the order of the subtraction here, and the resulting value can be positive or negative. Now that poses a problem when we want to try to calculate one numerical value to capture how much those data of those 30 numbers spread out from the average. And the reason that's problematic is because if we take all 30 deviation scores, so once again, if we have a sample of 30 numbers, and we calculate the deviation value for each of those numbers, and we add up all of those deviation scores, which is contained here in the parentheses in this lower equation, and we add up all the deviation scores, so we have our summation symbol here, it will equal 0 because half the scores will be positive, the other half of the scores will be negative. So that poses a problem, and there are ways in which that is dealt with, and we'll get to that here shortly. The term average deviation, or the concept of an average deviation, works us towards the variance and standard deviation scores that we'll eventually calculate here. So an average deviation presents an overall picture of how each score deviates from the mean. Once again, if we have 30 scores, this eliminates our need to try to visually determine a pattern by simultaneously examining all 30 deviation scores at the same time. So what we can do is we can add up all the deviation scores and subtract it by n, where n equals the total number of participants, the total number of cases that make up our study. Now, the problem here in trying to calculate an average deviation is what we saw on slide 27. The average deviation will always sum to 0. And that's because in our numerator, the sum of the deviation scores will sum to 0. Therefore, 0 divided by n will equal 0. And that's because the scores are balanced around the mean. Approximately half the scores will be positive, approximately half will be negative. And so the way in which this was dealt with, two scientists almost 100 years ago debated how to deal with what's called the zero-sum problem. On the left-hand side, Sir Arthur Eddington came up with the suggestion that when we calculate the deviation score for each case in our study, then we just simply take the absolute value of each person's deviation score. Taking the absolute value eliminates the negative sign, and we can then calculate an average deviation. Sir Ronald Fisher came up with another idea, and he thought that if we take each score's deviation and we multiply it by itself, we get a squared value, then that carries out the same purpose. It will eliminate the negative sign, and so we can then move forward with additional calculations. And so approximately 100 years ago, this debate centered around which of these two techniques should be used. Now, the squared deviation is the method that was retained and moved forward in subsequent developments in the field of statistics. And it was determined that in terms of calculations, the squared deviation proved to be a more efficient way of dealing with how to calculate variability than the absolute deviation, and that it produced a smaller error under ideal conditions. The squared deviation is easier to manipulate algebraically, whereas if we just take the absolute value, we would not be able to gain a sense of the directionality of those deviation scores. We wouldn't know which one was below average or which one was above average. And inferential statistical techniques that were developed following this debate were subsequently based upon the squared deviation. So the equations here to calculate the standard deviation and the variance are listed, as you can see here, and I will take a moment and go through these. Now, if we have real data from a sample, we want to get what's called an unbiased estimate of population variability. So eventually we're going to use the standard deviation to imply some sort of inference to the larger population. And so what we see here on the left-hand side in the upper corner of the slide, this is the equation for variance. So S squared, sometimes you see the X as a subscript, sometimes you don't, depending upon the textbook that you read. But the lowercase s is the symbol for standard deviation, and the S squared, the squared standard deviation, is called the variance. Now, what you see up here on top is the technique suggested by Sir Ronald Fisher, where each score is subtracted from the average, and that's each score's deviation, and then it's multiplied by itself, eliminating the negative sign. And then all of those squared deviations are added up. It's then divided by a term in the denominator we simply refer to as n minus 1, and I'll detail that here in a moment. Now, the problem with the variance calculation, S squared is the variance, is that it produces units that do not make sense because it's a squared unit. But the genius of squaring the term allows us to eliminate the zero-sum problem, and then algebraically we can bring it back to a standard deviation in the original units here on the right-hand side by taking the square root of the entire quantity. And so even though we've multiplied it by itself, each score's deviation yielding a squared term, square rooting the final answer will bring it back into the original units of measure. And the n minus 1 is referred to as the degrees of freedom. And so where n is the sample size, and if we have a sample of data, we would divide the sum of the squared deviations in the numerator by 19 if our sample size was 20. And so this produces what's called an unbiased estimate of the variability that's reflected of the population. Now, what about sigma? Sigma is the symbol for population standard deviation. So recall that when we see the Greek letters represent the population. Now, if we happen to have data from the entire population, we wouldn't need to divide it by the degrees of freedom. So what we see here is if we actually have the parameters from the population average, which is represented by the Greek letter mu. We take each score in the population, subtract it from the population average or the population mean. We square that value. We do that for all the elements in the population, add them all up, and divide it by the size of the population. That gives us the population variance. And on the right-hand side, we carry out the exact same mathematical operation as we did with a sample, is that when we take the square root, then we bring back the units into the units of the original measure. So that ends this video on the measures of variability, and in the next video, we're going to detail how to actually carry out the calculations.